This video is designed to help you understand, number one, how to graph an absolute value function, but also how to understand transformations of functions and how we can move them around, and it'll actually apply to many of the functions we research later on this year. So first thing we want to understand is, what does an absolute value graph look like? So that later on we can move them and bend them and shape them and kind of play around with what that shape does. Well, any absolute value function, again, is just a function. So let's just pick some numbers such as 0, 1, 2, -1, -2, and we'll just plug them into a table. Remember that an absolute value function doesn't really affect most numbers as long as they're already positive numbers. So if we plug 0 into our absolute value function, we just get 0, which means I can now plot the point 0, 0, input and output, directly in the middle of our graph. The same thing happens to any positive numbers. If we plug in 1, we get 1. If we plug in 2, we get 2. So at 1, 1 and 2, 2, we're basically just getting a linear line that's going to travel with a slope of 1. But the change comes in when we take the absolute value of negative numbers, such as the absolute value of -1 or -2, because we get back positive numbers. Remember, it's their distance to 0 is now the output. So -1 being 1 unit from 0, technically we input -1 onto the x-axis, but we output +1. So we're no longer going to follow that nice diagonal line. We're actually going to get a different diagonal line traveling up and to the left from that origin in the center, with a slope of -1 technically. So we get that nice V shape. And that's the shape of an absolute value function. Input to output. The inputs can be essentially all real numbers, domain of all real numbers, but the range always comes out that y is greater than or equal to 0, because your absolute value is always greater than or equal to 0. Now, what if we change some things around? What if we multiply outside of our absolute value, or we do some adding and subtracting inside and outside? This is where transformations come into play. And what we need to understand is, what is the effect of having a number, a constant a, multiplied outside? Also, what are the effects of subtracting a number inside or adding a number on the outside of our absolute value function? First of all, remember that a on the outside is a multiple, so it's going to be actually stretching. It's going to create distances that are greater or less than comparable to the distances we already have, close to 0. So the first thing we want to realize is A can be a vertical stretch or shrink affected, or that affects the width essentially of that V shape we normally would have had. So if we normally have a V shape, again, traveling at that nice diagonal on our graph, well, if we put in this 1/2, 1/2 will be a vertical shrink. If you take all of our y values, all of our absolute value outputs, and multiply them by 1/2, essentially they're going to be half as high. Instead of going up 1 unit, we're going to go 1/2 a unit. Instead of 2 units, we're only going to go 1. Or instead of 4, we'll only travel 2. And we essentially would get a line half as high in both directions as the original. Now, oops, that's a bad idea. What else can a do on the outside? Well, if a, instead of being a positive number, if a comes up as a negative number, it can also create a vertical reflection. Better put in or shrink here, depending on the size of the number. But it can also create a vertical reflection. If it were negative, again, +1 as an output would become a -1. And essentially our V shape would flip over. We'd kind of get a V shape going this way instead, if that were a negative number. Well, notice that up here, this is going to be a vertical reflection, because we are going to have a -0.5 up there. Now that was a bad thing to write, because the way my computer is organized, I need to get rid of that first. So now let's write in that this is a vertical reflection. Now, What are h and k going to create? Well, remember, if multiplying stretches and shrinks and reflects, if I add 3 units, I'm going to be sliding, or essentially k, adding units on the outside, takes all of my outputs, and it's just going to make them larger or smaller, or k creates a vertical shift. So I'm going to take my blue line again, and I'm going to shift it up 3 units. Well, and if adding on the outside creates a shift vertically, adding on the inside will create a horizontal shift. Now realize that happens kind of backwards. If x minus 2 is up here, anything where I would plug in 2 normally and have been over here to the right, to create that same effect, I'm going to have to plug in an even larger point. So what I used to get at 4, I'll now get at 2. So this is actually going to be a shift to the right 2 units. Even though it's subtraction, it's going to create sort of a backwards shift. Or the vertex, essentially, of our V-shape is going to be created by h and k. H being an x minus h, and k being whatever is added on the outside. So what I can do is go up here then and say, well, plus 3 means I'm going to move up 3 from where my original was. Minus 2 is going to move me to the right 2 units. And there's where my new vertex will be. Now all of the other points technically would also move up 3 and right 2, but they're also going to be affected since they're no longer zeros inside of our absolute value function. X being 2 created a 0, and 0 times negative 0.5 really didn't get affected. All of my other points, though, will be affected by that vertical shrink and reflection. So where I would have moved a half a unit up, but actually a half unit down instead, I'm now going to shift that point up 3 units and right 2 units. So it's essentially going to create a slope that's half as large, like we talked about before, but also traveling downwards. So the V shape is going to look much flatter with a vertex at 2, 3, but also traveling downwards. That same idea, like I mentioned, can also be applied to any other function. So if we're taking a look at what we have here, the function f of x is on our graph, and that's a different shaped function. Notice I have it redrawn on each one of my graphs already. All that's going to be created by adding 3 or adding 2, remember these are shifts. So this is going to be a vertical shift up 2, and that plus 3 will be a horizontal shift left 3. Remember, adding is going to go to the left. So what I need to do is take my original shape in green, or in red here, notice in green underneath it, and what I'm going to do is shift it up 2 units and left 3 units, and that red shape would be my new function. The same thing will happen down here. 2 times f of x, well 2 is again a vertical stretch, because anything multiplied by 2 is going to get twice as tall. Well, if I take my function, if I can click on it here, instead of being up at 2 units, I need to stretch this to 4 units, but also instead of being down at 2 units, I need to stretch that down to 4 units. Notice what was at 0 never moved, because 0 times 2 is still going to stay at 0, but 2 units up becomes 4, 2 units down becomes 4, 1 unit down became -1, and essentially we've stretched from the x-axis everything twice as tall. Now a negative on the outside is going to be a reflection, so I redrew that here. Notice I've reflected everything. All negatives became positives, positives became negatives, but then also remember that -1, so that's a vertical reflection, -1, remember, is also going to be a shift horizontally right 1. So I need to take my red line, now that it's flipped over, and I'm going to move it right 1 unit. Again, those same ideas can be applied to absolute value v functions. So take a second, go ahead and pause the video now, and see if you can't place each one of these graphs properly on the coordinate grids. It may help to write down the shifting and stretching next to your function before you draw. Okay, each of the graphs is kind of illustrated here. Notice that all of the addition on the inside, anywhere there was addition or subtraction inside, created a horizontal shift. All of the vertical shifts, up or down, are noted on the outside. Note the two with the negatives in front with the a values are pointing downwards. Also, the slopes of the right side of each graph are also given by that a value, because remember, that's that vertical stretch or shrink. So 1/2 created a 1/2 slope on the right here. The -2 created a -2 slope on the right side on this side. And that -1 technically created a -1 slope on the right side of this V shape. Let's see if we can't do it without actually graphing. Feel free to check them on your calculator after you do them, but see if you can describe the three shifts and use proper order of operations. Think about PEMDAS. What happens first when you get to this last one? Okay, each one of the answers is given to you here. Again, addition on the outside is a vertical shift, so we're going to travel up 3. Subtraction or addition inside is a horizontal shift, and remember, subtraction actually creates a shift to the right, so you're going to go right 5. Remember that we multiply before we add, so you would want to vertically reflect. Then, since we're adding on the outside, it's also a vertical shift up 2 units. On the final page, I'm going to see if you can't go backwards. Just a little bit of a challenge for you. Think about where the vertex is for describing your shift, but also think about the slope of that right side to think about that a value that you're going to put out in front of each function. What I want you to do is try to write a function to fill in all the gaps for this basic idea. What number would you put in front, and what would you create for h and k as far as your vertex goes, inside and outside your absolute value function? Take a second to think about all 4 graphs, and I'll put up the answers in just a minute. Okay, you'll notice that for each of the graphs shown, I went ahead and found the slopes of the right side. If you look at where the initial point is and try to estimate approximately where another point on our graph would be, you'll notice here that we move 3 units to the right and 3 units down, creating a slope of -1. So that gives us a number to put out in front of our function. Since our vertex was directly at 0, 0, we didn't actually need to write in those zeros. You could write it more simply, as I did in blue, as y equals the negative absolute value of x. Or it looks just like our V shape, only flipped to go downwards, reflected over that x-axis. Again, all the slopes are given to you. I try to describe where those were. Also, all the vertices are labeled. As you noticed, if we move to the right, we traveled 2, 0, which created that -2 to travel to the right 2 units, but I didn't travel up or down at all here. The 2 vertices at the bottom are also given, and their equations labeled. If you have any questions about those, talk to your teacher. But otherwise, good luck with absolute value functions, and remember these transformations, as they're going to help you again further down the road with many other functions. Have a great day.